Einstein's special theory of relativity. A full description with main points.
Albert Einstein's special theory of relativity, published in 1905, revolutionized our understanding of space, time, and the relationship between matter and energy. This theory introduced groundbreaking concepts that challenged traditional notions of physics. Here is a full description of the theory, along with its main points. 1. Principle of relativity. Einstein's theory begins with the principle of relativity, which states that the laws of physics are the same in all inertial reference frames. An inertial frame is a reference frame that moves at a constant velocity, without any acceleration. This means that there is no preferred or absolute reference frame, and the laws of physics must apply uniformly across all inertial frames. 2. Invariance of the speed of light. Einstein proposed that the speed of light in a vacuum, denoted by c, is constant and the same for all observers, regardless of their relative motion. This concept challenged classical physics, which assumed that the speed of light was influenced by the motion of the source and the observer. 3. Time dilation. One of the most famous consequences of the theory is time dilation. Einstein showed that time passes more slowly for an observer moving relative to a stationary observer. This means that as an object's speed approaches the speed of light, time for that object appears to slow down from the perspective of a stationary observer. 4. Length contraction. Similarly, Einstein introduced the concept of length contraction. An object in motion will appear shorter in the direction of its motion when observed by a stationary observer. This effect becomes more pronounced as the object's speed approaches the speed of light. 5. Relativistic mass increase. Einstein proposed that as an object's speed increases, its relativistic mass also increases. This means that the energy required to accelerate an object becomes larger as it approaches the speed of light. The formula E equals mc squared encapsulates this relationship, where E is energy, m is mass, and c is the speed of light. 6. Equivalence of mass and energy. Perhaps the most famous equation in physics, E equals mc squared, demonstrates the equivalence of mass and energy. It states that mass and energy are interchangeable, and a small amount of mass can be converted into a large amount of energy. This concept has profound implications, as it underpins nuclear reactions and the energy released in such processes. 7. Relativistic addition of velocities. Einstein derived a formula for the addition of velocities that accounts for the effects of special relativity. Unlike classical physics, where velocities are simply added, in special relativity, velocities do not add linearly at speeds close to the speed of light. This formula ensures that the speed of light remains an upper limit for all observers. 8. Mass-energy equivalence principle. Einstein's theory also introduced the mass-energy equivalence principle, which states that the mass of an object is a measure of its energy content. This principle has profound implications for our understanding of the fundamental nature of matter and energy. 9. Causality and spacetime. Special relativity unified space and time into a single entity called spacetime. Events that were considered simultaneous in one reference frame might not be simultaneous in another due to the effects of time dilation and the invariance of the speed of light. This challenged the traditional notions of causality and led to a deeper understanding of the interconnectedness of events. In summary, Einstein's special theory of relativity introduced a revolutionary framework for understanding the nature of space, time, and the relationships between matter and energy. Its main points include the principle of relativity, the invariance of the speed of light, time dilation, length contraction, relativistic mass increase, the equivalence of mass and energy, relativistic addition of velocities, the mass-energy equivalence principle, and the unification of spacetime. These ideas have fundamentally shaped modern physics and have been confirmed through numerous experimental observations and technological applications.